We are still in Notes 1 of Unit 10, and we're still doing motion along a curve. Today, our problems will entail the use of a calculator. All right, so I'm continuing in my notes that I just left off from yesterday, and we're down here at example 8, and we all have a calculator in our hands. All right, now I will tell you that your calculator has a function, a mode. It has a mode for parametrics, okay? The only time that you would go to parametric mode is if you just couldn't stand it and you had to see the curve. We can do every one of these problems without going and looking at the curve though, all right? But if you ever just can't stand it and you really want to see the curve, then go and do parametric mode, okay? After you have satisfied your desire to see that curve, go back to function mode. Do not stay in parametric mode, all right? So you'll always see me, I'll never go to parametric mode. Well, I shouldn't say never, but not to work a problem I won't. I'll just stay in function mode, because we can do every one of these problems without going to parametric mode. All right. So we have our calculator. We are all in Radian mode, right? Radian mode. Okay. A particle moves in the xy plane so that x is this function of t and y is this function of t, where t is between 0 and 2 pi. I love it when they give me a range of values for t. What distance does the particle travel between the two x-intercepts? What distance does a particle travel between the two x-intercepts? Well, first of all, they're telling me that there are two x-intercepts. What's going on in the curve when we are at an x-intercept? What's happening when there's an x-intercept? Well, we have an x-intercept when y is 0, right? That's when we cross the x-axis, when y is 0. So, well, let's set y equal to 0, and that will give us our times between those two x-intercepts. So I'm going to take my y and set it equal to 0 and solve it for t. So I'm going to get sine of t when I bring 1 over and then divide by -2. I get sine of t as a half. And between 0 and 2 pi, that gives me that t is pi over 6 and 5 pi over 6, first and second quadrants, right? So I have my times that the curve crosses the x-axis, and now I want to find the distance the particle travels between those. So distance, remember distance, that's the one that we developed using our old arc length formula. This is the integral from pi over 6 to 5 pi over 6. Remember, those are our times, right? Because we have a dt out here. Square root of x prime squared plus y prime squared dt. That's your formula, all right? Now, for the sake of the FRQ part of this, and I know it has a calculator, but you're going to need to say what x prime is and what y prime is. Because right now we don't know. We haven't been told that, so you can't just assume that AP knows that you know that. So come in and find x prime and find y prime. X prime is 4 sine t. Y prime is -2 cosine t. And now it's calculator time. So, oops. All right. Math 9 for integral, pi over 6 to 5 pi over 6, square root, big square root, parentheses, 4 sine t, close the parentheses on the x, close the parentheses on the 4 sine x, and then square. Plus, parentheses, I don't really need that negative because I'm squaring, right? 2 cosine t, close the parentheses on the t, close the parentheses on the, I just did one too many, close the parentheses on the 2 cosine x, and then square. Dx. So we got 7.347. 3 decimal places at least. You can give me more, but not fewer. Every year I have somebody who keeps giving me 2 decimal places, and I take off every time. Hopefully by the time the AP exam rolls around, that's fixed. Okay? All right. Example 9. In example 9, we have a multi-part problem. ABCDE, multi-part problem. Okay. I need you to know something. And I need you to know that for a multi-step problem, you always want to put x prime in for y sub 1 in your calculator and y prime in for y sub 2 in your calculator. We can get a lot out of that. This is big bang for your buck. X prime and y prime. Even if you weren't given it, go put it in. Like in the previous problem when we were given, where's my previous problem? In the previous problem when we were given x and y, if this was a multi-part problem, I would have come and put x prime and y prime in for y1 and y2. Okay? It's just by far the most useful. So always do that. Okay? So let's start there. In this case, they gave us x prime and y prime. So in for y1, I'm putting x prime, where I'm letting my calculator's x be the t. And in for y2, I'm putting cosine of t squared, where I'm letting my calculator's x be the time. Okay? Now, another very useful function. Another very useful function is that square root. Remember that square root one? So you want to put the square root of x prime squared, but remember x prime is your y1, and then y prime squared, but y prime is your y2. You want to put that, this will make your life a little bit nicer if you do that. You don't have to do this, but it'll make your life nicer if you do. And I'm going to store that in for y sub 3. And when I'm doing this section every year, I just leave that in for my y3. My y3. Okay? So in for y3, I'm going to put square root of y1, remember that's under alpha f4, y1 squared plus y2 squared. And that's just convenient to have. It just keeps me from having to retype that in a couple times. Okay? All right. So I do that before I really get going on the problem. If I have a calculator in my hand on a multi-step problem, and I know I'm dealing with parametrics, I do that. Okay? All right. So we are given x prime and y prime, and then we're given an initial position. So we're given that x at 2 is 7 and y at 2 is 4. We're given that. So since we have the velocity vector and we have an initial point, we can find any other point. So I'm guessing that at some point we'll need to find a position. All right, part A. Write the equation of the tangent line to the curve at the point where t is 2. Okay, point and slope. What is the point where time is 2? They gave it to us. The point is 7, 4. That was nice. The slope. Slope is dy dx, right? Which is dy dt divided by dx dt. Dy dt they gave us was cosine of t squared. Dx dt they gave us was sine of t cubed. And now we just want to plug in time is 2. So dy dx at time 2 is equal to cosine of 4 divided by sine of 8. And I think I can just leave it like that. If you want to get a decimal, great. If you just want to leave it like that, that's fine too. Either one. Safe stop. This is an FRQ, so I like to safe stop. So my equation will be y minus the y coordinate is equal to the slope times x minus the x coordinate. And that's it. So even though we had a calculator, we didn't need it for this one. I guess we could have used it for that, but we didn't have to. Okay. Speed. Speed of the particle at time 2. You need to know that the speed is the magnitude of velocity. And the magnitude of velocity is that square root of x prime squared plus y prime squared. No integral, no nothing, just that square root. So the speed at time 2 will equal the magnitude of the velocity at time 2, which will be, okay, this will be, here's my notation for that. Same thing at time 2, right? That's what we put in for y3. We put the speed or the magnitude of the velocity in for y3. So on your home screen, we can do alpha F4 and go grab our y3 and evaluate that at time 2. Remember that will evaluate your function at that value. So we get 1.18, either 5 or 6. I'm going to use, I like to round, so I'll say 1.186. Okay? Remember, never just write a numerical answer without saying what you did to get it. Okay? Part C. For what value of time between 0 and 1 does the tangent line to the curve have a slope of 4? We want the tangent line to the curve to have a slope of 4. Okay? And then we want to find the acceleration vector at that time. All right. Well, for the tangent line to the curve to have a slope of 4, we need to find the slope and set it equal to 4, right? Well, dy dx, we already said what dy dx was up here in part A. All right? Dy dx was cosine of t squared divided by sine of t cubed. And we're going to set that equal to 4. How can we solve that? Calculator time. Calculator time, right? In your calculator, I'm going to turn off, I'm going to turn that one off, I'm going to turn that one off, I'm going to turn that one off, because I don't want to see those individual. I don't want to lose them, but I don't want to see them on the graph. What do I want to see on the graph? I want to see dy over dx. So I want to see y2 divided by y1, right? So in here I'm going to put y2 divided by y1. Now there's two ways to do this. I can also put 4 down here and then see where these two intersect, or I can put 0 here and put -4 here, and then I'll see where these two intersect. Either way is totally fine. We know that we're looking for between 0 and 1. Guys, go to your window, limit your window between 0 and 1. There are so many times I'll be going around helping students in class or in tutoring, and I go over and look at their screen, and they've got like from -10 to 10 on their screen, and they're trying to only look between 0 and 1, and it's hard, okay? Why are you making it harder for yourself? Go and limit yourself to where you know you want to look, okay? Otherwise, you're just making it hard for yourself. Since I'm only looking for where this y sub 4 crosses the x-axis, I can just make sure I have 0 in between my y's, and I know I'll be good. So I'm only seeing between 0 and 1. And there it is. Second Calc 5. Enter, enter, enter. And that's the time. The time is 0.616, right? That's the time, but now I need to use that time, and I want to use the entire decimal. If you don't use the entire decimal, then your next answer might not be correct to 3 decimal places. So I'm going to right now go in and save that x value, that time. I'm going to store that in for some letter. Okay? And now I want to find the acceleration vector at that time. So the acceleration vector at that time is equal to the second derivative of x at that time, the second derivative of y at that time, right? Now that's what I'm doing to get my answer. So I've told AP what I'm doing, and now I'm going to use my calculator to do it. So I need the derivative of the first derivative at that time for both x and y. So I need math 8 because I'm taking the derivative. Derivative of y1 at that value of x, so at a. That'll be the x coordinate of my acceleration vector. And then I'm just going to arrow up, go change y1 to y2, and I'll have the y coordinate. So the x coordinate is 1.109, the y coordinate is -0.457. Okay. Part D. Find the position of the particle at time 1. This is where we're going to set up 2 fundamental theorems of calculus. So we have the position at time 2, and we have the 2 components of the velocity vector, so we can find the position at any other time. So x at time 2 minus x at time 1 is equal to the integral from 1 to 2 of x prime. Okay? So x, we're looking for x at time 1, right? So x at time 1, do the correct algebra here, it'll be x at time 2 minus the integral from 1 to 2 of x prime of t. Now, I don't need to rewrite what x prime is because they gave me x prime. If they give it to you, you don't have to rewrite it each time. Okay? But if they had not given it to me, I would have had to say what that was, if I had not done it previously in the problem. So x at time 1 will be, x at time 2 was 7. I should have gone ahead and done that in the previous step, but that's all right. Now time for our calculator. So I need 7 minus the integral from 1 to 2 of x prime, which is my y1, dx. And there's my x coordinate at time 1. Okay, y coordinate, we'll do the same thing. Y at 2 minus y at 1 is the integral from 1 to 2 of y prime dt. So y of 1 will be y of 2, which was 4 up from my problem, minus that same integral. So calculator time. 4 minus math 9, 1 to 2 of y prime, which is my y2, dx. So 4.443. And so now the position at time 1 is, and now I look at how they gave me the position. They wrote it with an ordered pair, so I will write mine with an ordered pair. But if I chose to use some chevrons there, that's really okay too. They would accept either for that. Okay? Alright. Last up, find the magnitude of the displacement of the particle from time 1 to time 2. Remember magnitude of displacement? That was where we found the length of that, of the change in distance. So this was just delta x and delta y, so this was the square root at delta x squared plus delta y squared, right? So I need to find delta x and I need to find delta y. Delta x is x at 2 minus x at 1. And I just found both of those. I just found x at 1 and I was given x at 2, right? So x at 2 was the 7 minus x at 1 was my 6.782. But I want to use my entire decimal here. So that's delta x. I'm going to put dot 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 just to show you that I'm using the whole thing. But for AP, you could just round it to 3 here. You can write it rounded, but you need to use the whole thing. Delta y is y of 2 minus y of 1. Same thing for that. So that's going to be 4 minus the 4.443 number. So this is negative 0.44306 dot dot dot. Okay? Alright. Now my magnitude of displacement, I think I'll write that over here. The magnitude of displacement will be the square root of delta x squared plus delta y squared. I need to say what I'm doing here. I'd never ever just want to give a number without saying what I did to get it. So I'm going to have the square root of parentheses. I'm going to go grab that 0.218 number squared plus delta y squared, and that will give me the magnitude of the displacement, 0.494. Okay? All right. And that is the notes for day 2. So get practice putting things in your calculator. Get practice giving AP what they need for you to get full credit for the problems that you know. All right? Okay, go practice.